All right, so this week we are going to be talking about plate tectonics. So specifically our goals in this lesson are first to understand what's meant by a scientific theory, then to explain the interior structure of the Earth, to identify the major processes of plate tectonics, and then to use plate tectonics to explain the current distribution of landforms on the Earth and predict their future development. So we're starting off by talking about the concept of a scientific theory. So the everyday meaning of the word theory is it's like a guess or a proposal. It means that you're uncertain about what you're saying. So for example, I've been watching the Amazon Rings of Power series, and my theory is that the Meteor Man is Gandalf. And so that's a guess. We'll see what happens later in the show, whether or not I'm right or some other theory that somebody has about that character is correct. But that's not the way that we use the word theory in a scientific context. Right? My guess as to the identity of this character in the TV show is more like what we would call a hypothesis in a scientific context. Although to be a real scientific hypothesis, it would have to be testable. And, a theory about a character in a TV show isn't really testable. You just got to wait and see what happens in later episodes. So in a scientific context, when we say theory, we can use this definition from the American Association for the Advancement of Science. It's a major scientific organization across all different scientific fields, and they define a theory as a scientific theory is a well-substantiated explanation of some aspect of the natural world based on a body of facts that have been repeatedly confirmed through observation and experiment. So a theory is an explanatory framework to talk about the world. It tells you why things are happening the way they are. Right? That's the important thing about a theory, is it tells you why. It gives you the reasons for how things are in the world. And a scientific theory is based on, as they say, a body of facts. So it's something that's well supported, that we have lots of evidence behind our theory. And the only way that a theory is going to get overturned is if we come up with a better theory that explains all of that existing evidence and some additional evidence that the old theory couldn't cope with. So a theory can help us generate a hypothesis, and then we can test that hypothesis, and that will either confirm the theory or help us refine the theory and improve the theory as we move forward. So plate tectonics, which is our topic for this lecture, is sort of the unifying theory for geology over the last half century. It is the theory that ties together what people are doing in all different aspects of geology. It helps us understand why all these different geological phenomena exist, how they fit together. So this is kind of comparable to the way that the theory of evolution is a unifying theory for the discipline of biology. Right? Everything in biology connects in some way to evolution. Evolution helps tie together all the different, more specific aspects of biology. Plate tectonics does kind of the same thing for geology. So by looking at plate tectonics, we can sort of see how a scientific theory comes into existence and becomes accepted by the scientific community. So I'll move out of the way of his face there. So this is Alfred Wegener. He's a German earth scientist who proposed a theory that he called continental drift back in 1912. And so the evidence that he pointed to for this idea was first that the shapes of the continents fit together like a puzzle. So it looks like the continents used to somehow be connected to each other because their coastlines match up. And so the Atlantic coasts of Africa and South America are the most obvious example there. You just look at a world map and you can see the parallels of the coastlines of those two continents. But if you spend some time sort of piecing things together, you can find a bunch more ways that matches up, especially if you're looking at the actual geological edge of the continent, which may be, underwater, doesn't match the coastline necessarily exactly. So you can see all of these pieces kind of fitting together like a jigsaw puzzle. And then if you fit things together that way, you'll also see that rock formations and the distributions of certain fossils now line up nicely. So you'll have a rock formation, you have a particular type of rocks in a certain sort of arrangement that are, for example, in South America, and they run up to the edge of South America, and then they pick up in the part of Africa that would match up with South America when you fit them together. And with all of these different ways that we would fit these pieces of continents together, you would see those rock formations going basically across the gap from one continent into another. And then likewise with the distributions of fossils. And so that's what's shown in the image I have there, that there will be some sort of fossil creature that's found on both sides of that place where you fit these continents together like a jigsaw puzzle. And so that would suggest that at some point they were actually connected to each other so that these creatures could walk back and forth across between these two continents that are now in the present day separated by a large ocean. So Wegener noticed this and saw how you could fit these things together, and so he proposed that the continents had drifted over time, that they moved across the surface of the Earth, that they were not always located where they are today, but they have been moving over the course of hundreds of millions of years. So this was the proposal that he put forward back in 1912, and most geologists at the time rejected his theory. They said, no, this isn't a good theory, because he couldn't explain how or why continents would move. So he had this suggestive evidence that made some sense if you thought that the continents had moved around, but he couldn't explain why would continents move. You know, why would South America, this gigantic landmass, just kind of plow across the surface of the Earth? And how would it do that? Like, what's the force that's moving a continent across the surface of the Earth? So he didn't have an explanation. His theory was incomplete. And so it actually made a lot of sense that other geologists did not immediately accept this theory, that they said it's got problems, we're not going to buy it until we can get a more complete picture of what's going on, right? A fuller explanation of the phenomena that we're seeing in order to have a theory that we can accept. The additional evidence came in over the course of the 20th century. So the idea of continental drift as proposed by Wegener developed into our current theory of plate tectonics. So plate tectonics is kind of the modern name for this theory. And so some of the evidence that helped to fill in these gaps in Wegener's theory and provide the mechanisms, the explanations that he was lacking included things like seafloor data. So what you're seeing in that map there is the age of the rock at the bottom of the ocean in different parts of the world. And what you'll notice, and it's really obvious if you look down the center of the Atlantic Ocean, you'll see that right along the center of the ocean, sort of exactly halfway in between the Americas and Africa and Europe, you've got the very youngest rocks. So there's super new rocks that have just formed right along the center line of the Atlantic. And then as you go out from there, they get progressively older and older and older. And so then the oldest rocks that you get to on either side are the same age, right? You see those rocks that are about 100 million years old right along the coastlines of Africa and South America, right where they would match up if you fit them together like a jigsaw puzzle. So this showed that the way that continents move, right, the mechanism for continents moving is that we get new ocean floor forming in between them and then old ocean floor being destroyed somewhere else. Okay, so the continents are not just like sailing across the top of the Earth, that the outer portion of the Earth is being created and destroyed at different places, and that's what moves the continents around, right? So that fills in part of that gap, the unexplained bits of Wegener's original proposal. We also had seismic data that helped us establish what's going on inside the Earth where we can't see. right? Everything in the interior of the Earth that, again, Wegener didn't really have a good understanding of based on the information available at the time. We've now been able to get a much clearer picture of what's going on inside the Earth. And in next week's lesson, we'll talk in more detail about seismic processes. So seismic means having to do with earthquakes. We'll talk about that in more detail and see how that data helps us understand what's going on inside the Earth. But for now, just understand that we got this much better picture of the interior of the Earth that helped us provide a mechanism. So what is moving these continents around? Why would a continent move from one place to another? Once we understand the interior of the Earth, we can explain that, fill in that gap in Wegener's theory, and that's why since about the mid-20th century, geologists have come around to accepting plate tectonics as this unifying theory for the discipline. So let's take a look inside the Earth. So the diagram there, you get that little pie slice with the different layers labeled. They're not to scale. They've exaggerated the size of especially the outer few layers so that you can kind of see what's going on. And then the little Pac-Man shaped part shows you the different layers to scale. So the outermost layer of the Earth is the crust. It's a solid layer. It's between 3 and 30 kilometers thick, mostly made up of silicon and oxygen in various sorts of mineral combinations with a whole bunch of other less common elements to it. And the crust is the only layer of the Earth that people have actually been to. So our deepest holes don't go past the crust. So when my wife was a little kid, she learned about the interior of the Earth and decided she was going to try to dig a hole down to the mantle. Got a bunch of the neighborhood kids to help her try to dig this hole in their backyard. They got a couple feet down before they got in trouble and had to stop. And I told her when she told me this story, I was like, well, don't feel so bad. Nobody has ever dug all the way down to the mantle. So you didn't make it when you were a little kid, but nobody else has either. So that's the only layer that we've actually directly seen. But using various sorts of other data, we can figure out what goes on below that crust. So the next layer down is called the mantle. And so that goes down up to about 2,900 kilometers into the Earth. And the mantle is defined and distinguished from the crust by its chemical composition. So it has fewer of the light elements like aluminum, that's one of the other constituents of the crust. It has more of the heavy elements like iron. So the chemical composition distinguishes the mantle from the crust. But then within the mantle, there are 3 sublayers defined by their structure. So we have the upper mantle, which is solid. So we have this solid layer at the very top of the mantle, and the upper mantle plus the crust, these 2 solid layers on the outermost part of the Earth, we refer to as the lithosphere. So that's going to be an important term that we talk about, the lithosphere. So that is this solid shell around the outside of the Earth made up of the crust and then the upper part of the mantle. Then the middle part of the mantle is called the asthenosphere. So the asthenosphere is molten. So the rock, when you get into the asthenosphere, is so hot that it is no longer fully solid. It's not fully liquid. It's kind of a tar-like consistency. So it can move, it can flow, not quite as sort of thin and easily flowing as something liquid, but it can move around. So that's that middle layer of the mantle. And then the lowest part of the mantle, the lower mantle, is solid again, because even though it's incredibly hot down there, there's also a ton of pressure on it. And so the pressure solidifies that lowest portion of the mantle. Then inside the mantle, you've got the core. And the core is, again, defined by its chemical composition. It's mostly made up of the really heavy elements like iron. They sunk to the center of the Earth as the Earth was forming. So now we've got this giant blob of iron and other heavy elements in the center of the Earth. And the core, again, we can divide into 2 structural layers. The outer part of the core is liquid, so like fully liquid. It's so hot that has melted. And then the innermost core, the very center portion of the Earth, is again solid. So these are the layers that make up the interior of the Earth. Right, so we've got our solid outermost layer, the lithosphere, made up of crust and upper mantle. Then we've got the asthenosphere, which is our molten layer in the middle of the mantle. Then we've got the solid lower mantle, liquid outer core, solid inner core. And for plate tectonics, most of the action is happening between the lithosphere and the asthenosphere. Those are the two layers that we're going to be most interested in talking about plate tectonics. So our crust on the outermost part of our Earth comes in two types. And if we actually go back here, it's illustrated in this diagram here. You can see that part of that crust is much thicker. You've got the sort of mountains drawn there and stuff. That's our continental crust. And then you've got the much thinner crust there where they put the ocean over. That's our oceanic crust. So that diagram sort of shows you the difference in those two types of crust. We've got that continental and oceanic crust, the continental crust being thicker, less dense, the oceanic crust thinner, more dense. So all the different parts of our Earth's crust are either continental or oceanic crust, and then attached to that solid upper mantle layer to form the lithosphere. So this lithosphere that covers the outside of the Earth is broken up into what we call plates. So rather than being a single solid shell, it's got cracks in it, and it's got these roughly 15 major pieces and then a whole bunch of smaller ones in between them as well. And these major plates generally have a combination of continental and oceanic crust. So if you look, for example, at South America on this map, the area that makes up the continent of South America is going to have continental crust below it. But then you see the South American plate in purple there extends off into the Atlantic Ocean a good bit. And so that side of the plate is made up of oceanic crust. So we've got a continental portion attached to an oceanic portion there. Same thing, North America, you've got a big continental portion underneath the land mass of North America. But then you've got some oceanic crust extending off into the Atlantic Ocean. So most of our plates are a combination of continental and oceanic crust making up a single plate. Then these plates move in different directions relative to each other and to the Earth's axis. That's kind of our 0 point. All right, our point of reference is the spinning axis of the Earth, and then the plates are moving around on the outside of the Earth in various different directions. And you can see that indicated with the little red arrows on the map there. All right, the different plates are moving in different directions. So you can see the Eurasian plate and the North American plate, for example, moving away from each other. North American plate going westward, Eurasian plate going eastward. Likewise, moving apart for Africa and South America. You've got plates moving together at other places. So, for example, the Australian plate and the Pacific plate there are coming together. So all these plates are moving in various different directions. So in order to understand how the movement of these plates is affecting the landforms that we see on the surface, we can look at what's happening at each of these different kinds of boundaries where two plates meet. So whenever two plates touch each other, you can have one of three things happening. They can be moving towards each other, they can be moving away from each other, or they can be moving side to side past each other, right? There's three basic directions that two things could go, right? They go towards each other, away from each other, or side to side past each other. So when those two plates are moving away from each other, we call that a divergent plate boundary. So down the center of the Atlantic Ocean, we have divergent plate boundaries as a very clear example of that. Two plates on either side moving away from each other. So the initial split that forms a divergent plate boundary can occur in a place that has oceanic crust or in the middle of a section of continental crust. And we actually have a new split, a plate breaking into two plates happening right now in East Africa. The eastern portion of the continent of Africa is in the process of breaking away from the rest of Africa. So this is a split that begins on a continent. And so at the very beginning of this split, you get what's called a rift valley. So we have the African Rift Valley running along the eastern side of, along the eastern side of the continent of Africa. And so initially this just creates a giant valley as the two sides move apart and the land in between kind of starts to fall down between them. But eventually, as those two parts of the plate separate, you start to get enough of a gap that molten rock is going to come up from the asthenosphere. It's going to cool and harden, and it's going to form new crust and upper lithosphere to fill the gap. Right? You're not going to get just an open hole down to the asthenosphere. That molten rock is going to flow upwards, or the lightest elements are going to rise to the surface. They're going to cool and harden and form some new lithosphere to fill in that gap. And the new lithosphere that's created is always oceanic crust. So you don't get new continental crust forming. When you have a divergent plate boundary, you get oceanic crust filling in between. So as the Americas and Africa split apart, rather than that just expanding the size of this continent with new continental crust being created in between them, instead we get oceanic crust forming in between them, this thinner, denser layer. And so the ocean water flows in on top of that, and you get an ocean separating these continents. So what that means is that oceanic crust is usually much younger than continental crust. So our continental crust tends to be very old, and it's just kind of moving and shuffling around on the Earth. And then you're getting oceanic crust forming new in between as continents move apart, and then being destroyed as things move together, which takes us to our convergent plate boundaries. So this is what happens when two plates come together. And, because we have a round Earth, anything that moves apart in one place, that's got to be coming together somewhere else. So what happens at a convergent plate boundary is going to depend on whether the crust on either side of that plate boundary is continental or oceanic. So you get a slightly different outcome depending on whether you've got continent or ocean on either side of this convergent plate boundary where they're coming together. So the first one, I should move my face out of the way here so that you can see the diagram. The first one is if we have ocean to ocean convergence. So we've got two plates coming together and you've got oceanic crust on either side. So that oceanic crust, remember, is thinner and denser. And so what will happen is one plate will get pushed down underneath the other. There's a process called subduction. So subduction means that one plate is pushed down underneath the other. It gets pushed down into the asthenosphere. And as it gets pushed down into the asthenosphere, the heat at that layer of the Earth melts it. So you get what had been this solid lithosphere gets pushed down into the asthenosphere, it melts. And so you get two notable landforms, two things that you can easily see on the surface that show you that this subduction is happening. So one thing you see is a ocean trench that forms right along the point where that subduction happens. Right? Where one plate's getting tucked under the other one, you get this trench in the ocean. Then as the subducted plate is pushed down, it melts. That melted rock then will come back up to the surface. It's made of lighter elements. So it's going to try to flow back up to the surface, and it's going to form a arc of volcanoes. So you're going to get volcanoes all along the edge of the non-subducting plate. Right? The one plate gets pushed down under, it melts. That molten material comes back up and forms volcanoes along the edge of the plate that's not getting subducted. And if these plates are covered in water, as the term oceanic crust would suggest, those volcanoes might eventually stick up out of the water and give you an island arc. So if you get a string of volcanic islands, then you are looking at a place where there's an ocean-to-ocean convergent plate boundary going on. Now, what if one of the sides is a continent? So if you get an ocean crust and continental crust coming together at this plate boundary, you also get subduction. And in this case, it's always going to be the oceanic plate that gets subducted. It's, again, thinner and denser. It's going to get pushed down underneath this thicker and less dense continental plate. And so you get, in some ways, a very similar outcome. You get this subducted plate going down, so you're going to get an oceanic trench at that point. And then the subducted plate is getting melted in the asthenosphere. The molten material is lighter. It's going to come back up to the surface. It's going to form volcanoes on the edge of the plate that's not subducting. The big difference here is because the non-subducting plate is made of continental crust, on the outer layer. Rather than getting a arc of volcanic islands, you're going to get a volcanic mountain range. Right? It's just volcanoes are forming on land instead of on the floor of the ocean. But it's basically that same process of subduction. One plate gets pushed down underneath the other, it melts in the asthenosphere, the molten material comes back up in the form of mountains. Things get a little bit different when you have continent to continent convergent boundary. You get two continents smashing into each other. They're both thicker and less dense. Neither one of them is really going to want to subduct under the other. And you can't really push one continent down underneath another. So what you're going to do is you're just going to pile up gigantic mountains as these two continents just ram into each other. So you get a lot less volcanic activity at a continent-to-continent convergent plate boundary, but you can get some really enormous mountains occurring there. So the largest mountains on the Earth today are the Himalayas. They're the product of a continent-to-continent convergent plate boundary. The Indian plate is smashing into the Eurasian plate. And we've got these two continents coming together and they're pushing up these mountains. The Appalachian Mountains running here through Pennsylvania are also the product of a continent-to-continent convergent plate boundary in the distant past. About 300 million years ago, North America and Africa smashed together. These two continents collided, and they created what were at the time some of the biggest mountains that the Earth had ever had. Mountains are much smaller today because that plate boundary has now become a divergent plate boundary. The Atlantic Ocean opened up, the continents reversed direction, and so the mountains are no longer being pushed up, and they've had a lot of time to erode down and become much, much smaller over time. But that's how those mountains originally formed, was as continent-to-continent convergence between North America and Africa. Two continents smashed together, pushed up these, what were at the time, gigantic mountains. So that is convergent plate boundaries. Our last type of plate boundary is a transform plate boundary. So a transform plate boundary is when the two plates are moving past each other, right? So rather than smashing into each other or pulling apart from each other, they're just sliding past each other, side to side. So at a transform plate boundary, because the plates are just sliding past each other, you're not going to have to create new lithosphere to fill in a gap. You're not going to have to destroy lithosphere as plates come together. So the main thing that you would see at a transform plate boundary is that any landforms that crossed that plate boundary, anything, a valley or a hill or something that spanned that plate boundary, as the plates move, would get kind of sliced in half, and the two sides would get displaced from each other. So as, say, a river crosses a transform plate boundary, it may make sort of a zigzag. Because the two sides of the river are no longer aligned with each other. And of course, human-built structures can also get moved out of alignment. If you build a road across a transform plate boundary, as those plates move, the two sides of the road will go out of alignment with each other. So transform plate boundaries are some of the least obvious ones just by looking at the landforms on the surface of the Earth. They're a lot harder to spot just visually by the landforms than the convergent and divergent plate boundaries. So let's look at a image from Google Maps on the satellite view. So this is something you'll be doing in your lab exercise. You'll be going on Google Maps, turning on the satellite view, because in this view you can actually see things that are indications of different kinds of plate boundaries. So I'm going to point some of these out to you on this image that we see here. So you see the United States and going off into the Atlantic Ocean. So we can see a divergent plate boundary here. So right by where the map says North Atlantic Ocean, you'll see that ridge running along the sort of north to south or northeast to southwest along the floor of the ocean. That's the Mid-Atlantic Ridge, and that is where that new lithosphere is forming as the plates to either side pull apart. So if you see a underwater ridge like that, then you know you're looking at a divergent plate boundary. Okay, so anytime you see a underwater ridge running down the center of a section of ocean, you're looking at a divergent plate boundary. Another thing that you'll typically see with these mid-ocean ridges like that, you see all these other fault lines running perpendicular across it, right? So all these sort of east to west fault lines, those are the result of how the plates are pulling apart. So that's another thing that will help you recognize a mid-ocean ridge. And you get this big mountain range down the center of an ocean, and then it's got all of those fault lines running across it. So very clear divergent plate boundary there down the center of the Atlantic. You should be able to spot some of those elsewhere on the Earth. Then down in the Caribbean, so if you look near where the Puerto Rico label is, you can see evidence of a ocean-to-ocean convergent plate boundary. So right there, you've got an arc of volcanic islands. And so our Caribbean islands, you get this chain of islands. Those are all volcanic islands. And then you'll notice that just off the coast of those islands, you see that big dark mark. That is a trench. So that is the point at which one plate is subducting underneath the other. So in this case, we've got the oceanic portion of the North American plate is subducting underneath the Caribbean plate, which is a small oceanic plate forming the floor of the Caribbean Sea there. So the subduction is happening right at the point where you can see that dark trench there, and then parallel to the trench, you get this arc of volcanic islands. That's what you're going to see when you're looking at a ocean-to-ocean convergent plate boundary. Then if you look over to the Pacific side of Central America, so if you look near where, say, the Guatemala label is there, you may notice another dark mark along the floor of the ocean. You've got another trench there. So that suggests we've got subduction happening. We've got an ocean plate subducting underneath another plate. And in this case, the plate that is subducting under has continental crust at that point. So we've got subduction happening there along the west coast of Central America and Mexico. So you get the trench on the ocean, and then you've got mountains that you can see on the land. And it's a very volcanic mountain range there on the west coast of Mexico and Central America. So you can just see from looking at the satellite view that you've got this continent to ocean convergent plate boundary there. Now, in this particular view, we don't have any continent-to-continent convergent plate boundaries that are currently active, though we do have the remains of a very old continent-to-continent convergent plate boundary. I mentioned just a little bit ago that the Appalachian Mountains here in the eastern United States are or were formed by a continent-to-continent collision. So you can actually not see them very well on this view just because there's too many state labels and borders in the way, and also the Appalachians are just very eroded down to a much smaller mountain range. So that's the kind of thing I wouldn't expect you to pick that out, not knowing the geological history there, because it's no longer an active plate boundary. But we do have the remains of an old continent-to-continent convergent plate boundary in this little view. So in your lab assignment, the things that you're going to be doing are, first, you're going to be recognizing the landforms created by these different kinds of plate boundaries. Right? You're going to be looking for these things like trenches and island arcs and mid-ocean ridges to help you spot where these different kinds of plate boundaries are occurring. And then you'll use what you know of plate tectonics to predict what's going to happen in the future. So if you start with a certain arrangement of plates and you think about where are they going to move, what's going to happen to them in the future, then you can use the theory of plate tectonics to project what our future landforms are going to look like.